Hi, my name is Sarah Kaiser, and I'm here to speak to you today about permutation and randomization in computer algorithms. Let's start off with a scenario. Say you're having an event and you're holding a raffle at said event. A large number of people are submitting in raffle tickets, and at the end of the event, you will pull one raffle ticket and whoever has the matching number will win a prize. Sounds great, right? However, people are concerned that the raffle might not be fair, that some people might be picked over others, or that the system might be rigged. So, what you decide to do is you decide to shake the box in order to shuffle things around and make as much of a randomization so that the people who submitted their tickets earlier don't have any advantage over the people who submitted their tickets later, or vice versa. How do we know exactly what random is to begin with? What makes something random? Is shaking a box enough, or do we need to do more, or less even? So let's start off by getting some definitions out of the way. According to Merriam-Webster, a permutation is the act or process of changing the lineal order of an ordered set of objects. The definition of random is related to having or being elements or events with definite probability of occurrence. So, in order for a permutation to be a permutation, it needs to be the original set with all of the same values and the same size. It just needs to be in somehow a different order. This can be only one element being changed, or it can be all of the elements being switched around. And in order for something to be random, it's actually very easy to determine if it is or not. It just needs to be a value that could equally be probable if it was any other value, such as a digit, or any other value in a set, such as a permutation. To help combine the two, any permutation, if we were to take a set of all permutations of a value, is equally likely to be a possible permutation. So, if we want to use computer algorithms to create perfect randomization, what we can do is we can take a set of values and do a permutation based off of a random number that is chosen, usually taking an element in the permutation set and swapping it with another based on random values. A very real-world application of this algorithm can be seen in patient trials. We'll use this algorithm to determine out of a group of patients which ones will receive a placebo and which ones will receive the actual medication in a fair and equal way. So for the program I've created to help demonstrate this concept, I've used 3 different implementations. A naive implementation, a more sophisticated implementation known as the Fisher-Yates shuffle, and the computer-generated one provided by the C++ library. This is going to be a visualization of the lexicographical implementation. So how this is going to work is we'll choose a random number between 1 and the end of the set, in this case 5, and we'll remove them until there are no items left in the set. The difficulty with this is that we will have to check each time to see if that value has already been removed. Currently it's going rather quickly. However, as we start to remove more and more values, the more times we'll have to search to reach our value, unless we get lucky, of course. Once the last value has been removed, these have all been placed into a new set in order from beginning to the last card placed. We're going to re-display these out as a new set, the first one being the first card we pulled. In my Fisher-Yates implementation, I take an n value, which starts at the last value in the set, and I treat it with a random value between 1 and n minus 1 of the current n. In that case, I trade that set, and then I subtract n by 1, taking the value smaller and smaller until the only card we're left with is the first card. The first determining factor should be that the input is not equal to the output. In other terms, that the output is a permutation of the input. The next factor should be that all of the outputs will be equal in length to the input, showing that no values were left out of the final answer. Okay, so now we're going to go through the demo. To start off with, I want to show you all of our input files for the program. So we're going to start off with Hoyle, which is the 52 standard bicycle deck. Then we have bingo, which is going to be every value that is possible on a bingo card. This totals up to 75 values. Then we're going to have our raffle, which is going to be a list of 2,000 different numbers that are all at least 6 digits. And then we have our patient trial, so this is going to be the list of patients I talked about prior. Let's go through the implementations. So we have our lexicographical, which should be the slowest, and this is that one I showed first in the card shuffle earlier. This is our Fisher-Yates shuffle, so this is going to be the second video I showed, so you can see that they're swapping each of the card values as we go through. And then we have our random manual. This is, again, the manual implementation of the random shuffle program. This uses the swap function. And then we have our random automatic, which is going to be basically the same thing as random manual, but it's done automatically through the random shuffle function in the std library. So now let's get on. We're going to hit build. Got that all good, and then we're going to run it, and then through this we're going to check on our program to see first of all the outputs, just check that those are all correct, and remember the way that they're going to be correct is if all of the items have an equal amount, and they should be equal to the input, which was 75, and they should have a shuffled value. So all of the values started with B in bingo, for instance. So if we see multiple Bs, we know that it didn't shuffle them properly, but in this case, we can see that they're nicely randomized. Let's just check all these other ones. We got Hoyle at 52, fantastic. 500, 500, 500, great. And then we have our raffle output, which is 2,000. It's quite a long one, so I'm going to skip this one. And then lastly, we're going to look at our timing file. So again, let's just check and see. We can see that our lexicographic implementation is going to be the slowest one. It's significantly slower than all of the other programs. And then we're going to look at our manual implementation, which is going to be the next slowest one usually. And then we have our Fisher-Yates implementation, which is a little bit faster. And then our auto implementation is very fast, usually clocking in at under 1,000 nanoseconds for all of these. I hope I've been able to emphasize to you the importance of perfect randomization and also explain a little bit better how it works. Thank you for watching.